Okay, can you hear me? Yes?
Yeah, loud and clear.
Yes.
We can.
Good. Good to see you. Today, I have a couple of things to show you. Oh, wait, I'm getting a. Because I'm streaming for YouTube, so I need to. Um, yeah, I was like listening myself after 1 second. So, um, today, session 4, I have a couple of things to show you, exciting ones, and talk to you a little bit about, because I received some questions um, from some of you about, for example, the drone scene. The drone scene is there with some modifications that I made yesterday, specifically regarding um, how do we use. Actually, I realized that I made a mistake, but it's fixed. But also, I want to show you that because it's a super complex thing because it involves physics, and also probably that's not the most realistic way of training a drone, because basically what we are doing is just applying, for example, for lifting one force. A more complex example that I'm planning to hopefully um, during the weekend complete is how can you, for example, apply forces in the motors independently, so you can basically do all the maneuvers. That will be actually the way to do it. And also, I mean, I realized that it was really ambitious to trying to train the drone like immediately. A good thing to do, let me see if I can show you here. Let me change. I will share my screen. Um, Let me share my screen first. Here. Okay. So it's to start training your drone with just like simple tasks. So for example, this one, uh, let me go to the script that I showed you yesterday. It is, just give me one small second. Drone. And if I go to here, I change actually the space type to continuous, because right now what I want to do, and you will see this in the script, and I can if you can check it, and I will explain uh, things if you want like later, or answer questions that you have later. Um, Yesterday we was just basing our actions on the integer that we were getting right from our um, vector action. So basically, if it was a 0, move up. If it was a 1, move down, and so on and so forth. So basically, it's something that I just deleted in this new script that is shared in the project. You can use both, but this one is based just in continuous action, continuous space type. So that means that you're getting float numbers that are continuous, right? And with that, you can control, for example, in a better way, you can control in a better way what's going on with your drone. So for example, um, one of the things that I did yesterday in the move up uh, function, I said that the up force was just like 450, but now I can have like, for example, like 100, a value like typical, and multiply by val, that is the parameter that I'm passing here. And val is basically my first continuous value. So it's a decimal number. And the only thing that I did just to show you how to incrementally, for example, train your drone, I just train it with the movement up. I just taught the drone how can you just like fly, right, to reach a target. And then you can start like adding, for example, if you move the target at random positions, okay, now how can you, for example, move diagonally or things like that? Just like uncommenting this and using the values. For now, I'm just going to show you this because we have a lot to cover. But for example, the drone is trained in a way that you should see it lift off. It's probably because it's too heavy. Let me change the weight of the drone. So the drone now, it's trained to reach the target every time. It just flies. It's just like a simple task. And you can see here what it says up force. It's always regulating the amount of force that it needs to apply so the drone can lift up. If I, for example, increase the mass of the drone, it will have more difficulty to do it, but it learns on how to adjust every time the force. And you see that it tries to go up, it tries, but it's too heavy. And then it just falls. So basically, I mean, because it's too heavy and I'm not giving enough force because the values are between minus 100 and 100. If I decrease, so these are the parameters that you can, I would say that you can tune in order to do this. So I'm expecting that you play with this. As I'm saying, I'm going to make this probably like a shorter video on how can you progress with these things. And also because ML Agents has a lot of things that probably we won't, I mean, we will not have the time to cover. To be realistic, this is, I mean, if we only had, so far we had 9 hours of training. That is like a little bit more than just one real workshop day. If you count that a workshop day is like 8 hours. So my commitment, because I'm interested in this and I try to maintain my YouTube channel updated, or maybe if I can organize another activity over soon, hopefully by the end of the summer, just before the semester starts, I can cover other topics. So for example, Gale, that is a generative adversarial imitation learning, and also how to configure something that is very important, curriculum learning. And that's something that you configure. So for example, you can train your agent in stages. So you start with giving the train, basically you set like some sort of like a syllabus for your agent, and you start with small tasks, and it automates the process of making each time this thing more difficult and changing parameters. You can automate that, but that is like a longer thing to do, and we will not have the time. But I'm just showing you this so you know that there is more to do in also the way you train something. It's good that now the drone like learns how to take off. I had some successful train attempts yesterday, but I realized that probably using a continuous space that I will show you also now at the end of this session, sometimes it's more pertinent than just doing discrete. So one more thing that I want to show you again, because today we're going to do our famous robot. I hope that you had the chance to model something. Let me connect through my other account because I have my Mac connected to that and I have everything configured there. I will stop sharing my screen and I will share the screen. I will mute. Can you hear me? Yes. Okay, so I will share my screen here. The desktop one. All right. So today, as I was saying, we will learn on how to calculate, for example, or how to train an agent to perform some tasks. So for example, grabbing an object and leaving it in another place, right? So we will do similar things to what I'm showing you here. So this is, for example, the calculation of a robotic configuration based on one algorithm that is called RRT, that is typically used for path planning. And this is something that it was part of a class that I had at MIT. So let me see if this is working. So basically this proof, I mean, the thing that we were doing, we were using inverse kinematics, but mostly we were calculating the path automatically using some sort of optimization to grab, in this case, the brick with the EWA robot simulation, then depositing that brick inside the cabinet. And this was like really cool because this simulation, then it was loaded in the actual robot. So this was like the last part of a project that I did for this class. And it had like several things like complicated, like calculating the joint rotations based on angular velocity, torque, collision avoidance, and so on and so forth, using mainly like gradient descent and other algorithms. So we will do today something similar, probably not that precise. We will try to teach our robot to pick and place, or simulate a pick and place, at least like an early version. So let me stop sharing my screen here. How can I do this for you? Just 1 second. Oof, I lost the. We will do this today. Stop video. Okay, I disconnected my Mac. So we will do exactly that. We will work based on one example that Unity is providing to show the new articulation system that they added to Unity 2020. And it's actually quite cool because it uses mostly NVIDIA optimizations to solve mesh collisions and basically like revolution joints. And it works perfectly. It's way better than any other system that existed in Unity before. I used to use, for example, what was the name? Final IK to try to simulate inverse kinematics and things like that. But sometimes it was giving me problems, so it's not the most optimal thing to do. Let me share my screen again. I will share screen 2. And I uploaded the necessary files to do exactly this. Basically, this is the simulation of a robot that I hope I loaded the thing. Yeah, I think I did. It will learn this. This was trained with like 4 examples. What this is doing is trying to first pick a brick. This is just a simulation because to do the actual like grabbing, using the gripper to grab something, and then it's like way more difficult. So we will have a simplified version of just like touching this and then just pointing like the drop place. So you can see that here it always picks a brick, and then it tries to, and then that target changes according to one of these points. So this is like a simulation of that. And we can do like cool things with this in terms of simulating, for example, instantiating game objects. So we are simulating exactly that. Trust me, it's like super difficult to train both things at the time, and probably that will be a week-long workshop. So we will learn first how to configure this guy. That is our robot. That it takes a while, so we will start immediately doing that, and then we will learn how to program it. We will use a robot controller. We will use more scripts that I put on the Dropbox folder, in the Dropbox folder, and we will work from there. The scripts are probably like even shorter than yesterday, but there are like several components that we need to take care of. So, and also we will learn on how to train this. Let me show you. I have. Can you see my console, my terminal window?
Yeah. Yeah, we see it.
So, for example, yeah, we will learn on how to start training this. And in the training, so you see when we start training, the robot just goes crazy because it doesn't know anything. And basically it will pick by joint how to actually do what it needs to do. That is like go to the brick point, touch it, and that will set a state of like pick brick, and then go and leave it in one of the other points that is there. But this is like, again, a problem with this type of I mean, it's not a problem, it's the difficulty with this type of algorithms that we're using. In this case, this was trained with PPO. You don't know if the arm, for example, will do things that normally, because the joints of the arm are completely unconstrained. We don't have limitation for the rotation of the joints. We don't have any limitation. So now, right now, the arm is just like even like clashing against the floor, is clashing against itself. So we are not taking care of that. But we can set a couple of constraints, for example, in code to, with rewards, enhance, for example, that the robot maintains a position as high as possible. So it doesn't do movements that are probably like dangerous if we're simulating this in real life. Also, we can set or force the robot to maintain the most of the time or get more rewards if it gets for the final joint, for example, a vertical position. Or we can dynamically set this to, for example, like a specific directions of our wrist of the robot or the end effector. So basically the angle of attack, basically it's different every time. We will show you today how to take care of maintaining mostly a vertical angle to pick and place. So for example, here you see that the robot is doing like whatever. Probably if I see this, yeah, the reward is not too bad, but it's still not great. It's like minus 0.2979. And I will also show you that you can use TensorBoard, for example, to look at the progress of your training, right? So you can see, for example, how is the cumulative reward evolving over time? How is the episode length? So for example, as the robot becomes like smarter, let's say, or more efficient in doing the task that you're giving, the episode length will be shorter. You can check the policy laws, for example, right? The Q values, or you can check also like the entropy, how random, for example, are the values that you're getting at the beginning, and how everything is basically, let's say, self-organizing. You can see the evolution of these extrinsic rewards. That's something that we will not talk in this workshop. Is also you can set now with ML agents intrinsic rewards. When we talk about extrinsic rewards, are rewards that have to do with the environment, right? That are outside the agent. but you can also have now intrinsic rewards that are some things that the agent that are internal to the agent. So for example, there is one specific that one specific type of reward that ML agents, like the people from Unity, added for solving like sparse reward tasks, and it's called curiosity. So it's like a curiosity-driven exploration, which is amazing. And it could be, for example, for a drone example, it could be great. It enables like basically just to explore, just like a child that is in a playground, for example, and he wants to and the child wants to explore the toys or things like that. You will also learn from that curiosity type of reward. I wish, I mean, we can do this like longer, more days in the workshop, but I know that everybody has things to do, but we will try to make this as complete as possible. If not, I swear that I will do everything more complete during the following weeks. Because at night I have more time, so I can record more like shorter videos, like 20-minute or maximum 30-minute videos that I can leave here, because the important thing is to share the knowledge. And again, I'm saying this now because for me, this is also an opportunity to know more people interested in this topic, so we can start talking after this workshop. Because in my group, I mean, no one is doing similar things at my group at MIT. They are doing like different things. And also in the robotics field, if you want to go to computer science, for example, for the project that I show you with this EWA robot, they are always like super busy and probably not too interested in things that had to do with design, for example, or construction. So they look at you and say like, yeah, that's cute. Maybe we can do something. And if they give you 20 minutes to use that robot, it's amazing. If not, you have to go and work with your little robot that you have in the headquarters of architecture. It's not like ETH that you have like amazing installations, or other places like, of course, CMU or whatever. So hopefully for me, this is a way of knowing more about your work and be connected in the future. Okay, enough talking. I will stop this guy because I don't need it anymore. I will put it on the side, and we will start creating an empty project. And let me arrange my screen here. Close TensorBoard. Sorry, I'm arranging my second screen so I can also see the streaming in YouTube, so I can check that everything looks okay for you on your screen. We will start with an empty project. My God, it's hot today here in Boston. And remember, before you do anything, hopefully you're using 2020 as a version or higher. And remember to go to Package Manager and just make sure that you have the ML Agents package installed. If you don't have it, just go to Packages, All, Write ML, and it will show up here, and you will see a button to update or install ML Agents in your computer. So we will create one scene first. That is called robot setup. And this will be a scene with just a robot, like the dumb robot, not doing anything. We will create like 3 scenes. One will be this, the other one we will add the manual input that Unity provides to do stuff with this type of robots. And finally, we will program our agent. But first we need to take care of this because this is actually quite cool. And we, again, we are going through this example of a robotic arm because, but it doesn't mean that you cannot apply it to like any type of revolution join type of entity, right? If you want to do an hexapod, if you want to do like whatever you want, you can use this. Again, remember the worm snake type example that that Unity gives you. It's basically is based on the same thing. So we will create a scene, and the first thing that we want to do is create just an empty game object. Right click, create empty. There's a chat. Can someone in the meantime share the Dropbox link? Okay, thank you. So so we'll create this, and we will call this my robot, or whatever you want to call it. And this robot will have basically the way it works when you make the a chain of joints. It will work like a cascade. You will have a parent object, and then you will have all the other things that you will add later. So first thing first, with my robot, we will start by adding one component that is called articulation body. And it's this one. And articulation body basically will give the information to Unity that this will have more articulations, right? This also indicates that this is the root of our robot. And we will add at the same time, because we won't focus on coding everything. In the Dropbox, I left, let me open the folder. Can you see the folder?
Yeah.
The screen? Yeah. So in the day 4, I left the scripts. So so you, I mean, heavily base and modify the Unity example, right? But some are untouched. So we want to import, we want to make inside Unity, create a folder, and we will call this script, or scripts actually. Again, we need to be organized, and we will add this robot controller here. That's the first thing that we want to do. Because we want to add this script robot controller, what? Rotation direction. Why is this giving me an error? We need to add another one of the scripts, otherwise it won't let us. I think it's this one. Let's try to add the following so we don't get that. Sorry. Let's try to add articulation joint controller and robot controller. Yeah, those two I think will be okay. Yeah, we are good now. So articulation joint controller and robot controller. Let's take a look. What are these? Let me close the drones from yesterday. So basically this script, I will explain just super fast. It takes care of controlling the way the rotations happen, selecting by axis. So basically you pass an axis, and then basically it's normalized value, and basically will tell, it has the functionality to make the joints rotate. It's nothing special. I don't want to waste time on this thing. So actually it was giving me the miscellaneous stuff. 1 second again, preferences. Visual Studio and regenerate. Okay, now it should work. And the articulation, sorry, the robot controller, not the articulation. Finish loading that. The robot controller, it will also allow me to for example, stop the rotation joints, also to rotate, sorry, and also to assign the different joints to our main robot configuration. So these are given. Again, we will not focus on that. So we will be until midnight doing stuff. So my robot will take this robot controller, and you will see that you have the possibility of specifying a length or a size for the joints that we are going to use. In this case, we are going to use 7. And we are going to use 7 because we're going to use like 6 axes for the typical robotic arm, but a 7 axis for controlling actually a gripper. That is also a prefab that comes with that example. That is good to have just because it looks prettier. You can have 6 if you don't want to include that one, but that's okay. We will use 7. One thing that you want to do as well is in the articulation body, just to set this to unmovable, immovable, and maybe you can configure the mass here. I mean, it's not mandatory, but you might want to do that as well, like set the amounts. I think it's in kilograms. I don't remember, I don't know that. But what are we going to do here? We need to configure each of the joints that we have for our arm. So we can start by just saying J1, for example, for the first joint, J2, J3, J4, you can do exactly the same, J5, J6, and the last one, we can call it just grip or gripper. And now we need to assign the actual game objects that we want to be each of those joints. So now we will create a new folder, and that folder will be called meshes. And in meshes, we will import I uploaded for you the Rhino model in case you want to use it, or you can use your own robot. I will use my files, the OBJ files. So what you can do, you can select the OBJ files. I don't know, why do I have 5? Let me see if I'm missing one. Anyway, I will import this, just drag everything here. And, oh, I know why. Okay, so you can see here in the bottom right part that we have each part of my robot. It's just a simple robot, very similar to like a universal robot, a UR10 or UR3 type of robot. You can have a KUKA that works as well, or if you find a KUKA model, or you can just do like pretty much whatever you want. Hopefully it's like accurate enough in terms of saying that one joint will be here, for example, for the mesh, and the other one will be connected here and here. So you have something that is consistent in terms of geometry, right? It's not that just like spheres that could be whatever. Because when we start building our robot, we need to start giving some precise location for this joints, basically. So the first thing is that will be to create another game object inside my robot, or whatever the name of your robot is, and we will call this J1. And here we need to specify, we will do it after this, a specific location with that joint, where that joint is, like the revolution, like basically the axis of motion is. But first we need to add some components to let Unity know how is this joint. So the first thing, we need to add a mesh collider, and that mesh collider will be convex. And right now it's kind of weird because we don't have anything here, but trust me, it will make sense now. We need to add an articulation body component. And you see that because this is not the root of our basically robot, our configuration, and this is the root, it has less options. This is basically the following link, so it has more information that we need to give. So we will leave this by default now. What we want to do is add the first, do this right, I think I did. I'm checking this is okay, okay, yes. We need to give now the first mesh of our robot. So we can drag J1 here. And actually we just care, we only want not this that says J1. We want just we just want the mesh that is inside. So what we can do, we can go to Prefab. If you imported the OBJ that I gave you, you can go to Prefab and you can say right click, you can do right click, go to Prefab and unpack completely, and then just move the default to J1 and just erase the J1, right? So you're just left with the mesh. And this is what you get, the first link of our robot. And it assumes a local position. So you see it's at 0, 0. This is at 0, 0. This is at 0, 0 because it's in a local position because of this guy. And this is also in a local position because of that guy. So this is okay. Now we can go back to J1 and we can press where it says snap anchor to closest contact. When you go to J1, it gives you here this option, snap to closest contact. And what we want here, basically you can set, you see that a new like axis gumball or like 3 arrows happen. So this will indicate where is that joint rotating. So in this case, we want this joint to rotate like this, right? So you see it's a little bit off axis because it just tried to, it performs like some calculation to guess where it needs to be. We will fix that. So we go to J1. It says that it is in the 0, 0. Probably my model was a little bit bad. Yeah, because it's trying to. So we can move this. Oh yeah, no, it's okay. It guessed well the center, but my basically when I rotate the body by like with the typical Unity like handler, it just rotates off axis. It guessed okay that is basically the position where this will rotate. So for now, this is okay. We can add other characteristics such as mass or things like that. We have information about speed. We will get information, and that is good because we can get this information also to, for example, if you want to communicate this with the software or with the robot that you have, you can do it. But one final configuration that we need to specify, that this is a revolute type of joint. And we will say that the motion is free. But look what's going on right now. It's giving, it's hard to see probably, but it's showing a disk here. Let me do a snap to closer. How can I change the, there's a way to change the, how it looks. For now, I don't remember. Well, whatever. You see that there is like some sort of red circle, right? But that red circle is just pointing like it's vertical. So we want to specify that this is horizontal. So we might want to set the parameter here, the anchor rotation, to 90. So now Unity knows that this will rotate horizontally. Basically, that disk indicates like the domain of the rotation. That you can also constrain here if you go to limited. For some, maybe I can do it here. I don't remember how to change that. No, these are the gizmos. There was a way to change the visualization of that disk, but I forgot how. Not here. No, these are just the properties. Anyway, it doesn't matter. Where was I? You can limit basically some stuff like the angles. So you can say, oh, you can only rotate like in a between like, I don't know, like 0 and 60 degrees. So that's up to you. In this case, we will leave it free. And now that we configured this, we are ready to add another joint. So we follow the same procedure. It's like pretty mechanic. So we close J1, and on top of J1, we right click, and we said create empty. And we will call this J2. And J2 is at the same level of the mesh that we have for J1, so don't worry, that's okay. And we will follow the same procedure. You see that it's in the, if these are folders basically, or this is a tree, it's at the same level, that's okay. We will add this articulation body for J2. And that's fine. And we will say a snap to the anchor to the closest object, but it won't show anything yet because we need to add, again, a mesh. So in my case, I will add J2 here. And because it comes directly from the Rhino model, it knows the coordinates. So it puts this in place where it needs to be. So we can give now the characteristics. This is revolute also axis. Right now, it's not giving me the right coordinates for that joint, so we need to position it. So the way we do it, basically it's in the same place as before. We can move this. So I can say that the position for this could be, and this is weird that this is giving me this. Wait a minute, something is not right here. This should give me, oh, I will do the unpack before checking that. I will put the mesh at that level and I will erase that one. So let me see why this is not snapping to give me, it's weird. So I can just try to approach if I manage this small
Maybe
gimbal here.
it's about adding a mesh collider. Could it be?
Oh, right. I forgot to add the mesh collider. You're completely right. Thank you for that. Because this mesh doesn't have a mesh collider. So thank you for reminding me that mesh collider. You need to add to the mesh a mesh collider that is convex, because you will see what's going to happen now. So if I go back to J2, yeah, now it's a snapping to a weird place. We will fix it. But the good thing is that once you select, and also I didn't add a mesh collider here. Remember to add to your mesh a mesh collider. You will see that the mesh collider is more complete. You see, it's basically considering everything. So again, so sorry for that. When you have the mesh, add the mesh collider here as a convex, and then add the mesh collider here.
So just a question, you don't have to have the collider on the J1 object?
Yeah.
So.
Yeah, that's a.
It doesn't matter. You can add it here as well.
But I think you have both now.
Sorry, I'm kind of new to Unity. Is that like, does it matter?
For this, it doesn't matter.
Okay.
You can add it here. I mean, I never had problems, but let's try to see. If I add it here, probably you are correct. Convex. No, because basically it's not considering that. You see, this has no mesh information, so it doesn't work. So I will remove it and I will add it here. Convex. So now I will snap it, and it tried to guess the center, but it doesn't have to be precise for now. You can do it like precise according to your model. I won't do it precise. I will just guess that this is the where my joint is, and I see that it's actually in the. Oof! I moved it. It snaps to exactly where the both objects basically are connected, right? So that looks okay. We will try to put this always in the proper angles. So because it does like some sort of adjustment, basically trying to align that that face with the gumball that is showing. We will say that this is 90 on the y-axis. This is 0 and 0, so it's facing the direction. Basically, is perfectly aligned, at least on the plane of this guy. Okay, so with that, we are again ready. We will configure these parameters next. We need to continue basically doing this. If you want to go faster, try to. It will be good. I will try to do it also faster, but I will show you this step by step. So another one, oh, not select children, sorry. I will create an empty. This will be J3. I want J3 here. I will unpack. I will move this guy here. I will erase this. I will add the mesh collider convex. So you see it has a convex mesh collider. I will add the articulation body to this guy. It's also a revolution type of joint. And if I say for this guy, sorry, for this guy, a snap, it kind of does a good job, not the best job, but we will fix this. So in this case, for J3, our parameters should be here in the anchor rotation 0, this is 90 and this is 0. And the position we will try to fix if we do 0, 0, 0. Where did it go? No, it was not 0, 0, 0, sorry. Here is 0, 90, and 0. And I will, again, like approximate the position of the joint. It's not a big deal, to be honest. Then you can do it like more precise. Approximate will be good. Basically, like precise will be perfect, but you will just get like a small off axis type of thing. I don't want to waste time on that type of things because it doesn't. I didn't export this with a specific pivot. I don't know if you can do that from Rhino. I don't remember, to be honest. So that's fine. We are okay with J3. Now, J4, very mechanical and boring process. J4. J4. See, this is like the one that does this movement. Unpack prefab. And remove this. Get rid of this. Articulation body. Mesh collider. Good. Snap. Close to contact. This did actually a pretty good job. So if you press the snap anchor to closest contact, it did like a very, very good job. And the C buffer doesn't let me, but it looks like center, so it's okay. Now, J5. And J5, this guy, unpack the mesh, this guy goes out, articulation body, revolute, mesh collider, convex, and it should be the anchor point should be there. It did a decent job, maybe not completely center. So we will try to move this more or less centered. It did a good job finding like the right angle for the joint. So that's always good. J6. Sorry if this is like a boring, long process, but it's good that you know how to configure it properly. And for J6, in this case, we will do something. Our J6 will be it will have the gripper. So how do we do this? So we will add to J6 an articulation body. And we will add the prefab that I left in the Dropbox folder. If I go to the Dropbox folder, if you go to the Day04 project, you can find a Unity package. And that Unity package has a prefab that basically is, it's like a block. I mean, we will convert our robot in a prefab, but basically it's like a ready-made block with information, with scripts and things like that. So this is a Unity package file. The way you import that package, you need to go to Assets, Import Package. Here, Assets, Import Package, Custom Package. and you go to the folder where the Unity package file is. This is a very good way to share files. I mean, actually, this is the way to share files with Unity, because you can select specific things that you choose what to share. You don't want to share, for example, like a log file. It won't allow you to do that, or crap that no one cares about. So you just say like open, and it will give you all the options. In this case, we have the articulation joint controller. It's giving us a warning, and the robot controller, so we won't do that. And actually, we don't import everything because those are the scripts that we are going to write and revise in this part. So I just want the pincher controller, the pincher finger controller, not the robot agent. And here the hand E variant prefab and the FBX that has the information of that prefab. So let's see how that goes. Just the pincher controller and the pinch and finger controller. And it's importing, and you will see that it will create by default the folder for the prefab, and you can pre-visualize it here in the lower right corner. It's just like a sophisticated creeper. You're going to use this because this is also automated to just to open and close, and it looks nice. You can do pretty much whatever you want. You can put any type of, oh, it says that it has some stuff missing. Probably one of those scripts. We can add it. Don't worry. Okay, don't worry. We will fix that. So we will add this the prefab, which we will just drag it here inside J6, but we need to locate it properly. So it's like really small, so we can scale it and locate it by hand. So we will say that this is 1, 1, 1 in the scale, probably 10. Let's see, 10.
Hugo,
Uh?
a quick question. Why in this case you're using the prefab and not the, because I imported and I also have the mesh of the hand. Is there an advantage of using the prefab instead of the mesh?
No,
Only for this component?
Because the prefab just has the behavior of closing and
Okay, so you're bringing more than the meshes.
yeah, this is why I'm saying that you can put pretty much any mesh that you want. I think it just looks cool, so this is why I'm using it.
Yeah, sounds good.
No big deal. So basically, just scale it to 3 more or less is the, and we will rotate this 90 minus 90. Basically, you give in the scale 333 is like an appropriate type of scale. And now you might want to align this to your robotic arm. I am cheating just for the sake of time. So you can put
I have a really basic question. How do you get into like the 2D view in Unity to drag it?
Usually I never work with perspective. I find it annoying. So just do if you click here on perspective, you go to ISO.
ISO, okay.
And then you go to 2D views just by clicking the arrows, like the ISO.
Oh, thank you. Oh,
because there is another 2D view that is this one, but that is for 2D stuff, like UI or sprites type of thing. So you see, I'm just using this because it looks cool, like the gripper, and also because it has already the articulation body controller. It has the mesh collider, and if I remember correctly, let me see which one is the script that we need to add. let me erase this. And oh, we need to add the articulation joint controller script. That is the one that was missing. But we didn't add this to any of our joints yet, so it's good. That's the next step now that our arm looks more or less. So also the gripper already has the right position for the anchor. So
Does it matter if the gripper is 90 or vertical like you have it?
it doesn't matter.
Okay.
I mean, you can configure that later. I mean, today we're not going to do like a specific gripping stuff. So you can set it like as you wish. So now, one thing that we need to add, one final thing, is exactly that missing script that the gripper had, is the articulation joint controller. So for each joint, basically J1, J2, J3, J4, 5, and 6 that has the gripper, you want to add the articulation joint controller. And this will have the information to control our robot. Basically, you can set the this to 100, like a proper speed, because you will see, we will use the manual input system that they provide, and you will see that it has like a lot of inertia. If this is like too fast or too heavy or whatever. We will set for now the stiffness of J1 to 100,000, the damping to 100, and we will leave all the other parameters by default. So we will copy this parameter for each joint now. Same here, we add the articulation joint controller, set the speed to 100, the stiffness to 100,000, the damping to 100, the articulation joint controller, 100, J4, we will do the same. Oh, in J4, I didn't have it as a revolution. That's good. 100 and articulation joint controller J5, same. Articulation joint 100 for J6. This is kind of tricky, but for J6, we will add, it's not tricky, we will add the joint controller 100. Let me see one thing that I'm missing here. It's a Revolut. Yeah, I was missing the right position for this one. This is again 100. And the hand gripper, we will leave the configuration as it is. It has like different parameters. So it has, instead of a mesh collider, it has a capsule collider. It's okay. It has everything configured, and it has some other things like the pinching controller. So basically it will simulate that it's pinching. Actually, it works. Unity provides with this model just an example that grabs objects that you can then check. It's fine. This is a little bit faster. This is with 300, but we can set it to 100. With this, we have our arm pretty much ready. If we see this, basically it gets all the collider. I will save the scene, but we need to configure other things. So I will add also a plane, not to the robot, but to the setup, to the main setup that to the main scene. A plane, that plane will be, for example, like 35 by 35, sorry, 35 by 135. The arm will not move, so don't worry if this is not in a precise location. So this could be 5. This is 11. This is 0. That's okay. Maybe a little bit bigger, 55, like that. And if you want, you can also use materials. So I will just give one color for each joint. And I think we're super good with time. So materials, and I will create different materials for our, for example, red. Another material will be blue. Green. Material orange. Magenta. And that's it. So blue will be blue. You just select the material, and in the inspector, you can change the parameters. Blue, let's paint this guy blue. Green. This guy here, we'll paint this green. Magenta, right here. The joints magenta. Orange, if someone wants to paint the robot orange, like a good Kuka or ABB, that's okay. Actually, this will be orange and this will be blue. Yeah, so this can be red. Okay, our robotic arm is finished, is okay and ready to be controlled. But we want to add the manual input. And once we have the manual input, we will have it ready for programming and programming this as an agent. We want the manual input because remember that I want to have I want to explain, probably I won't have the time to do it in these sessions, but I will send you a short video on how to do demonstrations so you can do imitation learning. So it's good that we also have, just like yesterday with the drone, we have the manual input for the robot. So also because it's cool to see it working. So we will create another empty game object, and we will call this manual input. We're using right now with this just plain like Unity stuff as they provided. And we will copy into our scripts folder one code that I gave you that is called robot manual input. It's in the Dropbox folder. It's called robot manual input. And it has some stuff that we will use a very simple script, but it will take the name of the joint and it will assign it to like a specific system input. And it will take that value and it will rotate the joint. So how do we do that? We go back to our robot. We will drag the robot manual input script to manual input. And we will provide the robot here. But first, what we want to do, we want to turn, because the robot is ready, we will not touch it. And if we touch it, we will just modify it as a prefab. To create a prefab and to share it maybe, or to just utilize it so you don't have to do everything again, how do you copy an object that you can share in different scenes, for example, or even projects? You just drag my robot that contains everything to the prefab folder. So now this is some sort of like block or component, like a Revit component, for example, or like a CATIA CAD part or project, whatever. So you can just like drag it to the scene and you have a second robot. And the second robot has all the characteristics. So you can use this again in another scene, which we will later. So I will erase that one. Now, this is a prefab. Now we can just drag my robot here. And if I press play, you will see that nothing will, oh, I need to adjust my camera also, but you will see that the robot somehow starts moving, starts doing something like a zombie, or if it's like it's drunk or falling asleep. It's like slightly moving. But if I press keys, nothing happens. I'm just changing my views. So we need to do one final configuration. And that final configuration, we will find it in, wait, just 1 second. You need to go here to project settings. And in project settings, in the input manager, you will find the axis. And you will basically configure all these parameters so you can control them. So how do we do this? Let me remember how to add a new one. Oh yeah, you need to just increase this number. We will increase it to 24 for now. So you see that cancel is repeated. So it just adds the last 6. Yeah, cancel is okay. It's just like a system default access. So it just repeats when you add more, it just repeats the last one. But we will change some things. So we will say that the second cancel will be named J1. We have to give this a basically the positive button. We need to assign, in this case, keys that we want to press so we can have the values. So we can have if you want negative values, for example, we can control this with the 1 and the 1 number in our keyboard, the 1 key. And for negative values here, we can just give the 2, 1 and 2, or we can say, I don't know, like Q and A, for example, controls the positive value of that axis and the negative value with A. That's fine. The dead zone and all of the other things, we will leave it as is. It's okay if it's x-axis. We don't care about that. And in the same way, I want you to configure all the remaining axes. So J2, for example, will be name J2. The positive button in my case will be W, and the negative, sorry, is negative button will be S, positive button will be W. You can assign like any key that you want. It doesn't matter. So J3, the negative button will be D, and the positive will be E. J4 will be negative F, positive R. J5. Sorry again if this is like boring and repetitive, but that's the way it is. That's okay. And J6.
Diego, maybe you get that wrong with J5. You write, yeah, negative, positive.
Oh, sorry. Thank you. T and G and J6, we want Y and H. And we can add one more actually for the gripper, just to see that you can control it. So we'll set this to 25 maybe. So we add a new one. I don't know where it added it. Oh, it added it here as a submit. Gripper. Did we call it gripper? Actually, you need to give the name of the, otherwise it will not find it. Should be, let me check one thing. So if you're done, if you're faster than me, that's great. I think that this one we can call gripper, that's fine. Nothing is tagged. Oh, and one thing that we will do also, let's just call it grip. And we will say that this could be like the negative value, it could be plus, and this could be minus. That's fine. One more thing and one final thing that we need to do with this, we configure all of our axes so we can have a keyboard input. We want to add also a tag. So if you select like any game object and you just like click on the drop down menu where it says tag, add tag, you can add new tags. So we want to J1, J3, J4, J5, J6, and the final one, let me see, how is it called? We can call it pincher. That's the way they call it in Unity. So just in case I'm creating this tags, in case we want to access this later. So pincher. That's great.
Is tag 0 already pincher, or do you have to have another one?
Oh, it was added. Sorry, it was okay. So you can add this to J1. I'm doing this just in case we want to then access some specific information about this. So it's a good way to have tags. So we can set like get element by tag, get object by tag, or by name. But sometimes with tag, if you have like a tag for different objects, so you can collect those in a list. This is just a good practice to have like something more complete. So J4 is on tag. So I think we're good to go. I think there's nothing missing. J6, let me see if that's the case. No, it's giving me some error. It's giving me one error. Yes, axis gripper is not set up. It's yelling me that there is one axis that is not set up. Probably the name was gripper. Oh yes, I know why. I call it grip, should have been gripper. I'll show you why. Hopefully this is okay now. It's giving me still in manual input. Whew.
Does it have to be pincher? Does it have to be named after the tag?
No, let me see why. Game object, let me see stuff on it. Let me check the old project that I showed you. Let me open it in my other screen and we'll be fine. We're also getting closer to the break, but for now, save the project for now, save the scene, and I will I don't want to get rid of the okay, just open the past project, the sample project that I have everything pre-cooked that I will upload for you. Let me see those inputs. Sorry for this. There's always something that goes wrong, of course. Oops, where is it? Project settings. I lost one of the, I lost the project set. Oh, here it is. It was hidden. Everything seems to be okay. Okay, what we can do for now, maybe in the break I will do it. Let's just remove the articulation body on the hand prefab, because for some reason it's not working. Let's just disable this articulation body. Let's just disable the pincher and the articulation joint controller. No, maybe leave the articulation body and just disable, if you uncheck this, the pincher controller and the articulation joint controller. That way, this should not call that, damn it. It's giving me again in manual input a mistake. This is weird and embarrassing at the same time. Whew. Manual input. Probably I'm missing something really, really stupid. Oh, yeah, also. Because we don't, this was the axis. Oh, I know why. I'm so stupid. Okay, no. I forgot one crucial step. Let's enable again in the gripper, the scripts. I forgot the most crucial part for our robot. Assign the parts. Look at that. So what we want to do, J1 goes to J1, J2 goes to J2, J3 goes to J3, J4 goes to J4, J5 to J5,
J2 to J3,
J6 to J6, and the gripper goes here. So now it gives me an error. Okay, now it's not giving me any error. Just let me set my camera in a good position.
Sorry, I think you just put J2 instead of J3.
Oh, another error, J2. Yes, exactly. Thank you again for that. J1, J2, J3, J4, J5, J6, and the gripper. So now, it's not doing anything. Why?
Should it move as slowly like this one, or you should jitter around like crazy?
Maybe it should move faster. Let me check one final thing, and we will be good to go. If this is the problem, also I don't think we need to do this, but I'm just gonna do it anyway. Let me just check. Maybe it needs uppercase for the axis. It's been a while since I did this, so let me just try with this one. I will say Q. It doesn't do anything. Let me try with 1 and 2, and here I will do 3 or 4, just to give an alternative. So if I press now, 1 and 2, 3, 4. Yes, it's going really slow. So it's moving, but super slow. So it is working. So we need to increase the speed of our object. So right now it's working. We will do that last modification. So maybe the speed should be, because for the mass, we are okay. We're using the gravity. Compute the parent anchor. Yeah, let's change the speed for each axis to maybe like 500. Maybe that's too fast, but who cares? We're just testing right now. Thank you for that, pointing that out. If this is not a thing, should be okay. It's a lot of configuration, sorry. It's hot, it's difficult to keep up with all of that. So yeah, it's the speed. So you see, if I press my buttons, I can move. Probably we should increase it more, but right now I'm just playing with my keyboard. So right now, I'm doing that. I'm moving that. So we have a functional robot. So do you see that the robot is like, kind of like a little bit, I don't know, it keeps moving. It has a lot of inertia. So there is a way to repair that, but we will do it later, actually. Because it has to do also on how this automatically calculates the mass of the robot. So I need to check that. Is there any question? Is it working for you?
Mine is working, but somehow I feel that some of the joints are limited. So for example, on joint number 1, I'm actually modeling a 7-degree of freedom robot, but on joint 1, it moves positive, but it doesn't move negative direction.
Okay, so one thing that you can do is, there is a thing, just like Unity thing. You might want to use the alternative button, alternative positive and negative, and see how that goes. And also, probably there's a difference in the gravity. Sorry, I hardly use these things in Unity, so I'm not very, this is one part that I'm not very good at. Yeah, also it has a lot of gravity, so we want to change that as well, so it's more responsive. Let me do that. Yes, somehow it works better. Let me see. I can share also the prefab with the all robot, but basically this is the procedure. Then you can spot the differences if you want.
Is there a reason why it's just like dancing around when you're not pressing anything? Like the controllers work, but it's just sort of like moving.
Yes, I was saying probably I missed one part of the configuration. I will check it because it's one parameter that we need to check, but I will do that during the break.
Sure.
So what we can do, we can have a 20-minute break now, return at 3:50, and I will solve this because probably I'm missing something. I don't know, but we're good to go because right now we can just focus on what's important and how to set up our robot and how to set up like some constraints, like basically what is everything about. Okay, so 3:51, we will return and we will do this. Okay, yay.
Diego, can I share my screen for a couple of minutes so you can have a look?
Ardavan?
Yeah, can I share my screen for a sec so you can have a look at this one and see what might be wrong here?
Okay,
let me.
Can you share it or do I need to give permission?
I think I can do that.
Okay, yeah.
So do you see it?
Yep.
Okay, great. So no, let me just, how can I, oh, okay, good. So when I play it, it is starting to make this game. And so you can see like joint number 1. So basically joint 0 is this fixed one, so it doesn't move. But this is joint number 1 when I'm hitting, Q and A. Only on the negative direction it works. Then on the, oh, something happened here that shouldn't have happened. I'll correct that one. But yeah, I think I just made a mistake about the location of that joint. I just editing it a couple of seconds ago. But as you can see, it was doing pretty well until like a couple of minutes ago. Maybe check it. But the main problem is that somehow it misses some of the motions. So yeah, I think that's the error here. So let me just.
Oh, so basically it's
Yeah.
it seems that it's like constrained, but
Yes. So the problem with the constraint is that like you see that it goes negative, but positive is somehow like capped on that location. And then like I'm holding the same button constantly, it stops there. Is there any physics involved? Like
yeah, I think it might be.
You see that it stops there. And then it seems that it's trying to rotate, but it stops there.
Can you decrease the stiffness?
Okay, so stiffness
And
is that
also-
number. Where's that stiffness? Here?
Yeah, and target should be 0.
Target? Where's that? Okay, so here?
Yeah, 0.
Okay. Okay. And stiffness should be something smaller?
Probably like 10,000.
Okay, good. So this was joint number 2. Oh, moves? No, way there. But still stops at that moment. You see that? And the target, that is something I'm not changing. It's automatically changing. So let me just manually change these numbers. So maybe 10,000.
With that. I'm just using by default what Unity provide in their sample. So
Okay, so let me see if I can get it to something meaningful.
let me check on my side why it's going like that, and I will be back.
Yeah, sure. Yeah, go ahead.
Ardavan, I have a question. How do you make your lighting look so much nicer?
Oh, it's just here. So you just go to lighting and then hit generate lighting. Basically,
Wait, where's?
So you might not have it. So go to window, rendering, and lighting. And when you hit that one, a menu pops up. Actually, this window pops up. And over there at the bottom, there's this button that says generate lighting. If you hit that one, that's going to solve.
Thank you. Oh my God.
You're welcome.
So much nicer. It's funny. Every time I'm watching the tutorial, I'm like, why does mine look so ugly?
Oh yeah. I was also facing the same problem. So I just Googled that one and said, oh, interesting. That's the solution. Okay. Welcome.
Thank you.
Mhm.
okay. G1, G2, 3. Hmm. It's okay. Should be okay as well. There you go. Maria, that was it. You forgot to add one joint controller, articulation joint controller. So can you hear me well?
Yeah, sure.
Yep.
So Maria, that was the problem. And J6, you forgot to add the joint controller.
Okay, got it, thanks.
Yeah. So in order to move forward, let me share my screen instead of that. Can you see Unity? Yes. No?
Yeah, we can see it.
Okay. So one thing that is, I don't know why, probably it was because of the model that I provided. It was too big. I realize now this is why the disk with the joint was like so big. So if you just go to your object, if you see that it's moving too slow, try to reduce the scale, because probably mine was in there's I don't know, I forgot which units are how to configure units in Unity. So for example, if I go here, I scale it down. Yeah, now I can see the right visualization of the joint, you see? So if I execute this, my arm moves the way it should. So it was too big. This is why it was also like kind of doing this stupid movement, like continue moving, because probably, yeah, the units from Rhino to Unity. Apparently Unity should be meters. So probably I did it in centimeters. So this is why it was too big. So if you just scale this, not the rest, and you should be fine. So just let me adjust my scene so it looks a little bit better. It's like very colorful robot. Let's do this to probably 2, 2. And put this in 0, 0. That looks better. So you see now, if I try to move my robot, it moves okay. Your robot should be moving like this. If it's a little bit off center, don't worry, you will have time to adjust that. So you see that this is perfect. Boop, 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 boop. It moves. You cannot move axis and like, because of the script that they provided. Probably I will try to modify it. So you can't move two axes at the same time, I think. No.
I have a question. Is there a way to switch to the scene? Because right now I can only control it in the game view. And when I switch to scene view, it just freezes. Is there a way to?
There is a good way to do that. Actually, you just drag the game tab and you put it on the side. So you click on here and you can see, is this your question, what you're asking? So for example, you see, I am.
Well, no, what happens is if, I might just, oh no, it's working now. Okay, yes, thank you.
Okay. But that's a good way also to see more stuff that is going on in Unity. You can just like divide your screen. There are some people that like to do this, for example, at the game here, because usually you waste a lot of space in this part. So that's also a good thing. So when
yeah, I was just asking because if you're selected the scene view, the controls break down, so you always have to select the game. Exactly. I thought it was a bug.
This is a good thing, and because you have the console, and usually you don't use this much of the screen for just to see the assets that you have. So I mean, actually, I work with this type of configuration. So our robot is ready. I hope your robot is ready too. If not, what I will do, I will select this. I will export my package. So you see, if I select the prefab, it automatically, and I said, I go to assets, export package, automatically it will select all the files related to that robot. So I will do that. I will export it, and I will put it as a Unity package called Awesome Robot. And in case your robot is not working, you will see it in a bit because it's synchronizing with the Dropbox stuff. So this should be actually smaller. 1-on-1 is okay. So now that we have this, we can program our agent now. So that's fantastic. We are good to go. Let me open my past project on the side. You can't see it, but it's just like a memory aid in case I'm forgetting something. We need a couple of things. Again, we want a target, right? So we will just close this robot tree, and we will add a cube. We will make it smaller. I will paint it with a different material, probably orange. And I will give it a size like 0.2, 0.2, 0.2. That's a decent size. And I will place it somewhere on the ground. Let's say 1, 1. No, -1. Now you can rotate your robot and orient it whatever you want. So for example, I can do this, and I can rotate this in 180 degrees. So it's facing X in this direction. It's up to you. So we will just put this cube here. And actually, this should be 0.5. No? Oh, sorry, 0.1. The height. So it basically stays on top of the floor. Maybe I want to create a final material. This will be a gray color, maybe a little bit darker. Gray. not to, did I change it? No. Okay, yeah. That's good. Because this will be our target. What we will do basically is just the same thing as always, just change the position, because we need to give like some randomness to the position of a target. So the robot wants to, or learns how to grab it, right? This is like the most basic thing that we can do. In order to do that, we have the target. We can specify also like predefined positions. So the way you do that, and I will show it, probably we will not use it at the beginning, but we will have this set up now. You can just do an empty game object. We will call it target positions. And we can add as many positions as we want inside this create empty. So basically, these are just empty game objects that I will call, for example, position 1, and we can copy this, for example, 10 times. It's just an empty game object that contains all these empty game objects. I will select the 10 if you click in the first, and then you click the left shift key in your keyboard, and then you click again, you select everything, and you can give here in the inspector where it has this cube, you can select, for example, a dot. Or in this case, for example, like this sort of diamond, whatever. So this will be an icon that if you press on gizmos, show gizmos, now you can locate this. It's a little bit big, so you can always reduce the size of that gizmo. So you see, this is just a position, and you can pre-visualize it. If you want to pre-visualize this on the game, you just click gizmos, the game view, and then you can position your positions to predetermine coordinates. So this is good, because imagine that you have like a pick and place type of thing and type of routine for your robot. You want your robot to learn how to pick and place stuff, or how to put like a wall together or things like that. You can just do this. And so, for example, place something here first, then here, then here, then here, then here, then here, then here, then here. You can predefine those things. So that is more just like typical, it's like typical, or like more coding that you will do in Unity, and has that behavior, or for example, that sequence of things is like a typical code not related specifically to ML agents. So you can also, for example, add some variations in height. The direction is a little bit tricky. It's not tricky, it's more complex. I keep saying that. It's more complex. You need to basically give like some sort of normal, or specify not a point, but a vector. So you can always have, for example, this and this. These two guys. I don't know which one these are. It's hard to select here. Like any two, like basically of these positions, and you can, instead of specifying the transform positions, you can basically calculate or create a vector with that direction, and then you can basically tell your robot, okay, like align to this direction. We will see now, because we will add a specific constraint for getting our robot as vertical as possible. So we will do that. Again, we will use this later not now. Once we have that, now we need to create our controller, right? We will do it the old-fashioned way, not as yesterday. Yesterday the intelligence was in the agent itself. We will do it separately, just because of convenience. And while I do this, Ardovan asked me yesterday, how does it benefit for having several agents? I ask people, I ask friends that know like way more about this stuff, and a guy that I know that works at Unity. And he told me that now they're implementing a new parallel training system. And he told me that, in fact, when you train many environments, because they change the academy and how the brain works, now you will train separate neural networks, but somehow they are still contributing to the learning. So if you have 10 like environments, you will train for sure faster. You will see that all your episodes like train faster, and I think that's better. I mean, a lot of things have changed. I remember that in the early samples, for example, when you open like the typical balance plane with the ball, the 3D ball sample in Unity, the more agents you have, it trains better for some reason. So, I mean, probably in the future, I will have a definite answer, because what I heard in future releases, they will release like a parallel training stuff with more options. So that's all I know for now. Okay, so ML agents. We want to do the typical things. It's just like creating an empty game object, calling it ML agents, and we will add a behavior parameters script, and we will call it my robot, for example, or touch cube, actually, we can call it, or whatever. This is the robot. Here is where we will do all the configuration. For now, we will say that this is a discrete space type. And for this, we will add 7. And for each branch, we will add 3. So it can give us like values from like negative, a 0, or a 1, if I remember correctly. Yes, I think I'm correct. For now, we will leave it like this. You will see why. And here, the space size, this will get more complicated. So you better start coding. The coding is there in the ones that I gave you. So I will have it on the side, because of course I don't know like all these lines of code by memory, but I will try to do it and explain it like as good as I can. So one sec, I need to open my notes. It's taking a while. Yes. Okay. So we will click here and we will say that this is a robot agent script. New script, robot agent. We will create and add it to our ML agents game object. So we double click here. It loaded correctly. So you see, if you see this assembly C#, you're okay. You will have the autocomplete and it will identify what is a game object and things like that. If not, go to edit, preferences. Usually what I do, I just change this to other. It will take like 2 seconds and then I change it back to Visual Studio and then I said regenerate project files. So when you open your script, you should not see here the miscellaneous type of stuff. So really quick, using unity.ml agents, using unity.ml ML agents that sensors. And just in case using system. So we can add access to other stuff just in case. It doesn't matter. Our robot agent is to inherit everything from agent. And we need a couple of things. So we need a public game object and vector, not separate. We can call it EE. We want also a public game object target. And also we want a public game object robot. Can do it like that, robot, or we can call it my robot. What else do we want? We want to also force this to have an orientation. So it will be, these are all public variables. These are, for example, orientation variables. We can call this robot controller. Robot controller, because we need to do that. We will have a touch detector. Call it touch detector. We don't have that touch detector yet, so we will add it soon. And that's it for now. Sorry, these are not the orientation variables. The orientation variables, this is a vector 3. And EE, we'll call it EE orientation. Is that okay? Yes. Vector 3 orientation. So now, when this starts, touch detector is not added. So before that, let's go to the folder. Sorry, yeah, and we will add the touch detector script that I put here. We will drag it to scripts folder. And also robot agent should go to the scripts folder. So we keep everything organized. So if we go back here, we'll reload a couple of things, save. Some things change. Oh, it lost the reference to the, let me close Visual Studio because you should not do that. Now I can drag robot agent actually. I made a mistake. Okay, now it's working okay. So you see, now it's not giving me error. It's giving me error with robot agent. Probably because I duplicated here. Yeah. I will drag the robot agent script later. It's yelling at me because I have it twice. So now I can drag it properly. Yes. Now I can open it. I'm sorry about this. This is a little bit problematic because I didn't save it first. Now, do you work? Oh, miscellaneous files. Reference by file extension. Now Visual Studio and regenerate. This should open the right one. Now, finally. And I will put this because these are my notes, the commented code, so I can. Okay, we want at the beginning to get the robot controller component from our robot. So we know that our robot name is my robot. So we will say my robot dot get component, and we will get the robot controller. Boom, good. So we can access that component. Also, we want the touch detector, the same thing. The touch detector will go actually to the target. So we will say target that get component touch detector. So first thing first, so we don't forget about that, we can go back to Unity. And to this guy, the cube, we can add the touch detector. So basically the touch detector will give you information if this was picked or this was dropped, things like that. So for this, we will call this, we will put pincher because basically it will detect the gripper. And it has a counter just to count a couple of things that is for debugging purposes. So don't worry about that. So we already have that. We can now start setting our initial conditions. So again, because now you're experts in doing this, we will say public override on episode begin to set the initial conditions of our agent. And this will be, we will add first a float, an array that is default rotations. And here we will just give an array of only zeros, right? For all of our axes. Remember that we have 7 because 1 corresponds to the gripper. So we will copy 0.0f 2, 3, 4, 5, 6, 7. And remove that comma. So these are just like float values to reset everything, all the rotations. And here, basically, because we are using one script from Unity, we need to call a method that is called in robot controller. We need to set robot controller is called force joints to rotations, and we will pass this argument that is called default rotation. So this will force our system just to reset everything. Also for our touch detector, because we're doing this immediately, we will say, not here, here, touch detector that has touch target, that is a variable that is there, we will set to false. What else? Actually, we can do this immediately. Remember that I added these target positions. In this case, I have 10. So we can just, in our script, so instead of just setting like a randomized position, that it will be better, probably for like better training, but now we want to train our robot just to go to different positions that then you can play with it and do other stuff. We will say, we will call this, how can we call it? I don't have it. Okay, we will call this target IDX equals to unity dot random unity engine, sorry, engine dot random dot range, and we will have it pick a value between 1 and 10. And actually, yeah, I forgot to add one more thing. That is, we need to add here an integer that will be called target IDX. Okay, if I don't remember if I should do it between 0 and 9, because yeah, we're picking from whatever. We'll do it like between 0 and 9. If there is an error, we can change it later. So we set that, and also actually, yes, because now we can say with this, target that position, sorry, transform that local position, and this will be equal to target positions. We don't have that yet declared. We can add a random one. Here we just fix always an origin position. Local position. And yeah, now that actually we can here set like variable positions or position variables. And one thing that we can do here, for example, we can create a region. So we can, actually I will do it here. So we can shrink this. It doesn't take too much space. Region, we can give it a name, but for now, I will say here, end region, not end if. End region. So in that way, we can collapse all the parameters. So the code is a little bit organized. You can do that with other methods. So what are we doing here? We will say that this is a public list and game object of type game object. And we will call it, first we will have one that is called orient points. I will explain what that is. And we'll say that this is a new list game object. It's an empty list. And we will also create a second list that will, well, we will give it the positions, target positions. And this is another list of game objects. So if I compile this code, it's not giving me, or it will not give me any error. It's compiling everything again. It should be done soon. Everything is okay. I can go back to Unity. And in Unity, now that if I select ML agents, I can start assigning things. Of course, I need to reassign the robot agent here. And for max steps, we will give 1,000. For the end effector, we will go to our robot and we will feed the variable, the prefab of the end effector. For the target, we will pass this cube that actually I want to call target. So let me collapse this again. ML agents, the target positions also. The target, we will assign the target. And for my robot, we just keep the full robot. And here, for orient points, we will set this to 2. And the target positions, we have 10. So let's give it 10. And we can do this like in a more efficient way. But in case you change your mind, I'm just showing you like the long way to do it. You just assign all the positions. You can just like say like, get me by name in a list, all the objects, but that's fine. I'm just setting this position 6, 7, 8, 9, and 10. Again, you can do this by script, just like saying that, give me all the objects with tag position, for example, and it will give it automatically. Now, these 2 elements, we will do the following thing. We need to go to our robot, and here in J6, we will add 2 empty game objects. So we right click here, we'll say create empty, and we will call this ORPT1 for orientation point 1. And here another game object, empty, sorry, here, that will be called ORPT2. Why here? Because you see that now this is just in the wrist of the robot. And orientation point 1, actually, why this gave me like different. Actually, I will just copy orientation point 2. So they should be positioned just in the wrist, but orientation point 2, I will move it forward. So with this, I will just determine like some sort of like normal, right, to the wrist. And that will be also like an observation. So I will keep an eye on that vector according to just a vertical one. So in order to visualize these points, actually orientation point 1 could be here. And I will do the same procedure of selecting both and adding just a point. Do you see it has a point? Actually, I will choose another color for the points. Let's do like cyan. And a little bit smaller icons. So yeah, basically this is a vector that I want to check later. Okay, back to our code, because we still have a lot of stuff to code here. We're done with the initial settings. So now we need to add our observations. And probably this is the most convoluted one. But also it's really cool because we will have a lot of observations. So the first thing that we need to do is to create a method. It's public override collect observations. We delete this line because we don't want that line. And we can say, first things first, we will say if robot controller that joints is, yeah. Oh, sorry, this is with small caps. Robot controller joints 0. That robot, is it robot part? Yeah, robot part equals null. Why is this giving me an error? Oh, joints. No, it's okay. basically, if there is no robot present, we check if we have the root, the first joint. If there is nothing there, just return. So we won't execute anything. Basically, if we don't have a robot, just return and do nothing. Now we need to add a float array for rotations. And we can say robot controller that it has a method to get the current joint rotations. So for now, again, we will get here 7 rotations. So 7 floats. So now we know that we have 7 floats from this. So I just added that node, and we will say that for each, how can we call this? Float rotation in rotations, in, not on, in rotations. We will normalize these values. So we will say that float normalized rotation equals to rotation, this rotation divided by 360 f modulo 1f. Again, I asked the person I know about Unity. He told me this is the good way to do it. So if you ask me specifically why am I doing this, I don't know much. I try other methods, and this was always working better for me, like the way to normalize. We will add this observations now. So we will say sensor that add observation, and we're passing 7 values. So we will add the normalized rotation. So we can add this to our sum of observations that we are giving to this agent. Now we need to also collect information, observations about the joints. So we will say for each joint in.
Sorry, Diego, one quick question. Are we doing this normalization for the learning purposes? So it's the same thing that we do always with machine learning?
Yeah, exactly.
Okay, got it.
Join in. So now we do for each var join in robot controller, again, sorry, the lowercase robot controller that joins. And here we will just add some information that will be helpful. So we control the robot not to go crazy, to go like extend a lot or things like that. So we will say sensor that add observation, and this will be joint that robot part that transform that position minus robot that, sorry, my robot that transform that position. So in this case, these are what we are doing is that we're getting information. It's a vector 3 information that is keeping an eye. So each part, the distance between each part and the transform of the main game object, because you don't want this to go too crazy that could cause errors. So in this case, we have 21 observations. Why? Because the information here will be, it will be vector 3. Basically, we want to keep like the vector information of those positions. So we will have 21 observations, 3 numbers per joint. That's good. Now we need to add another sensor that add observation. This is join that add, oh, sorry, join that, again, robot part that transform that forward. Yeah, that's good. Here, we will also have 21 observations. This will check basically the movement forward of the robot and backwards. So it will keep an eye also on that for each joint, right? So the position, like in that, if it's moving forward or backward. 21 observations. Then we will add sensor that, a new one, add observation. And we need to check the observation if it's like moving to the sides. That robot part, that transform. And for this, we can pick like any vector, left or right. It will be good as well. You can add as many observations as you want, but this is, I think, good enough. So this related to like joint observations. So I will add note here. Sorry, note, these are rotation observations. And these are joint observations. Now we need to add some observations relative to the cube position. So we can say the target position observations. Pretty much like the typical that we have done. This will be a vector 3. We will call it target position, and this will be equal to target that transform that position minus my robot that target that, sorry, transform that position. Actually, we can do local position. Should be fine. Or position. Let's go with position for this one. We won't train more than one agent, so that's fine. And we can add this sensor that add observation. This will be target position. Okay, so with this we have 3 more because it's a vector. And now we need to add information relative to the end position of the robot. So let's say that vector 3, sorry, robot end position observations. Vector 3 equals to end position equals to, we need the end effector. We call it EE. That transform that position minus the robot that transform that position. Basically, we need to have like some sort of way of looking where the end effector is at the end of each episode. And we want to do that relative to the main, like the rigid transform of our main object robot. So we can do sensor that add observation. This will be the end position. And also we can add here another observation according to that, not the robot position, but also relative to the end effector and the target. So we can say here observation target. Sorry, it was with uppercase, target position minus and position. Good. We're good with that. And also, if we want a specific orientation that we want for our robot, here we can do this and EE orientation. We call it 1 second. I'm trying to check one thing on my notes. How did I do it before? Just one second. We need to create, we have it here. It's EE orientation, actually. We already defined it. So EE orientation will be equal to orientation. How did we call it before? Orient points. We will get the first point 1. Sorry, this is the 0 element. Dot transform dot position minus orient points 1. This should be actually 1 and 0. If we're getting like something, we can switch it later. Yes, I'm okay. You will see why. Transform that position. So this is basically another vector that we will always try to keep vertical. So we need to add an observation about that. And what we want to observe here, that add observation, is not that vector, but we want to observe the angle. A lot of code. Angle between the EE orientation and vector 3 dot up, the vertical one. It could be down, but in this case we're doing the up. So we will measure the angle, right? So we will keep an eye on that angle. So we know that these observations will be always minimized. So I mean, in this case, we will try to minimize that. We will say a condition in our actions. We will say if the angle is bigger than 10 degrees, for example, you will get a punishment. So in that sense, now the robot will try to find like the proper orientations, but it will know, because we're giving extra information, that if at some point it will say like, why am I getting all these negative rewards if it's doing this, if it's going like, you cannot see me. Now probably you can see me. If it's going like horizontal, like super horizontal, and we don't like that, it will get like a lot of negative rewards. So we will punish it. And in that way, it knows that it needs to correct the behavior. So it's always vertical. So that is a good thing. And with that observation, we are done with the observation. So now we are good to code our actions. So now we do public override on action received. And again, I will provide the code for continuous robot. We will use discrete again. You will see why. Because basically the discrete will, you will see why. So we will do for int for I, sorry, for int I equals 0. Sorry, joint index actually we will do. Index equals 0. We'll say that joint index less than vector action dot length, and joint index plus plus, we will iterate over those actions that we have, and we will say that the rotation direction rotation, we'll call it rotation direction, it's equal to action index. How do we do this? Action index to rotation. Why am I not getting? I'm not getting the autocomplete. Should autocomplete this. Just 1 second. Probably I forgot to import a predefined script. Probably that's the case. Oh, let me go to. This is long, sorry, but it's, you will see if you check the video later, you will see that it will work really good. We have the articulation joint controller, the robot controller in our project. Let me see, articulation joint controller, robot controller. I have pretty much everything. So it should joint controller, pincher finger, robot agent, robot controller, robot manual input, touch detector. Let me see if it gives me an error or not, because this is what I'm supposed to do here. Does not exist. Sorry about this. Oh, yeah, because this is a method that we need to create. I'm so stupid. We need to create a method actually to map this stuff. So we will create this method that I have it here. This is this will give us the rotation direction, and basically we'll take the action index and it will return that action index -1. So we know that basically with which rotation we will, if we are going like, for example, negative or positive direction. This is just like a static method, and I will explain it later when we debug this, because this is a lot of, again, stuff that we are coding right now. So getting that rotation direction, now we can say robot controller that rotate joint, and here we pass the joint index, sorry, joint index, and the rotation direction, lowercase, and false, because if we see the robot controller definition, sorry, the robot controller here. To definition, go to object. How do you go to the object? Yeah. My input. Need to pass 3. Sorry, this I got a little bit here. Robot controller. So we were in the method, using the method that's called rotate joint. And if we check robot controller, rotate joint, basically it says that stop the previous joint from rotating. We'll say no. That's all. That's the thing. You can check the methods here if you open that robot controller script that I provided. For now, I will just close it. Those actions are okay. Now, we need
Sorry,
to
where did you define action index? In the new action index to rotation direction?
rotation. This here. This is a
Oh,
function.
I got it.
Yeah. So basically, it's like a public function rotation direction because that's what we need. And it's just like that's the way I made it. So I will leave it here. So now, I'm sorry, I'm a little tired of all this coding. So I'll put this here, this here. And here we will say we need to also do something about what happens when we touch the target. So we will say if touch detector that has touch target, and we will add a counter also. I mean, it's kind of silly what I did, but I just added a touch detector that there are more like clean ways to do this. This is what I came up just before the class, so sorry if it's not very neat code. Basically, if we check touch detector, it has a counter, and I'm saying that if it's just a way to check how many times I'm touching a target. So the first time I touch it, I will not end the episode, and I will just give it a specific reward. And when I touch it for the second time, I just give the big reward, because basically this is like the pick, like the drop position, and I just reset the target. It's ugly the way I implemented it, but that's okay. You can do it better for sure. So here we will say when that happens, basically when we touch the first time, we'll say add reward. Actually, we can say set reward, add reward. We'll do that. Add reward to 0.1, just like a small reward, because it has been a good girl or guy. And we will change now that transform that position equal to target positions, and here we will get the random number that we had before. Transform that position. So you understand what is going on? We touched the first time the target would change position. So now the robot has to go for a second time to pick. This is again like a just to have like a two-state type of pick and place type of training. So with that, we're okay. Now we need to here say that float. Sorry, I will extend a little bit. So probably a couple of minutes. Distance to cube will be equal to vector 3, 2, because we are almost in time. So it's not, we're almost there. So I will stand probably like 5 to 10 minutes. Distance, and we will measure now the end effector, that transform, that position, and sorry, I keep calling cube. This is target, that transform, that position. So we will get like an approximate, basically we're getting just the end effector. Actually, we can do here also one of the orientation points. Actually, that will be like any point that you put on the tip, but end effector will be fine. That position, and we will use that to measure and to give a reward based on that. Now, another thing that we want to do is to give a reward to the robot so it keeps like a high position as much as it can. So we will do bar joint height. So it doesn't give us like weird configurations where it's like crawling to pick the target or whatever. So this will be joint height equals to 0f. And we will say that for int, we will copy this loop for each joint that, I don't know why it gave me the vector. Actually, this is wrong. This is wrong, or this is right here. Oh, yeah. So here we'll just change robot controller dot parts dot joints, sorry, that length. We will iterate over the joints, and we will say like joint height plus, and we will add robot controller dot joints joint index, that robot part, that transform, that position, that y. Yes, minus target, that transform, that position, that y. So we will add just the position of each part in relation to in relation to the target. And finally, with this, we will say bar reward equals to distance distance to cube plus, basically we can add the reward immediately, but we're just setting like a compound reward for this one. And we will say this is joint height divided by 100, just a factor of 100. You can vary this if you see that the things are not going as you want. So finally, we can say that if vector 3, that angle between end effector orientation, so this was EE orientation, and this was our observation, right? That angle and the vector 3, that down. You can use up, but let's try with down. It was down. Yeah, I think it's down. It's okay. We want to measure that angle. yes, this is okay. Is less, no, sorry, is bigger than, let's say, 5. This will give us like a number in degrees. We can, oops, sorry, I spelled here a parenthesis. Whew. We can say that the reward, add reward, will be the current reward minus 0.1. So we are subtracting from the current reward. And finally, we will say that add reward will be equal to reward to reward. Then you can try a couple of things that you see if the rewards are too little, you can multiply this, or too big, you can multiply this by 0.1 or add things like that. So you can play with this type of stuff too. Not very scientific, but just like eyeball it a little bit. So that's okay. So with this, we have our robot ready to be trained. This is the end of the script. This is a cleaner version. No, you have the same version in the Dropbox, but you see it's like huge. So I compiled it. Everything, I will check that everything is in order. So I go to ML agents. I haven't set this orientation points. So those orientation points are here. So I will say that this is 1. This is the second element, or PT1 and or PT2. We don't have a brain, so that's, by this time of the day, I don't have a brain, but that's okay. So we need to get the space size for our observations. So if you sum everything, we have 80 observations. So that's a lot, right? It will tell you either case. I mean, it's okay if you count, but for example, if I say 90 observations, probably it will yell at some point, or in the debug, in the console of Unity, it will say that you are using 90 observations, but you only provided 80, right? So you need to, everything is being like caught up to that. So it will give you not an error, but a warning. And here, we didn't talk about stack vectors, but probably it's a good time to give information about this. They are not very explicit about this functionality, but what they say usually is that in the chat of Unity or ML agents, they say, we implemented stack vectors. What that is, you don't know. So looking information a while ago, like a couple of weeks ago, I found that if you want this algorithm or this code to also retain some information from past experiences, so also use past information to make new decisions, to have some sort of metric, you can add as many stack vectors here. So basically you will have the current, but also you said, oh, I want just to also keep an eye on the previous episode. And that could improve some metrics. It's like some sort of like recurrent neural network type of thing that is going on here. So now that we are pretty much ready to train our objects, we need to turn off the manual input. And I will add my config file. So I will create a new folder. I named it folder config. Oh my God, I'm tired now. So MIT Dropbox, where I had the Dropbox Digital Futures, day 4. Did I provide a config file? Probably not. Oh my God, I didn't provide the config file. I will provide it immediately. Just let me look for it. Here it is. And actually the name is wrong, so it's YAML. I will add a folder, config file. And I will add, just in case, also a config file with a different configuration. For SAC. For now, for this training that I will show you now, and we'll leave it up to here because this actually takes a while, and you will see that this is working. We will train with PPO, just as Unity sample provides. It will take a little bit longer, but it will give you also like good results. So now that we're ready, I will open. I have my console here. Can you see my terminal window? Now it's all blue and white letters, so it looks way better. So I need to check where I have this project actually created. This is it's on my desktop. So don't forget to actually enable your Anaconda environment, DF workshop, and I will go CD, and I am in my folder, CD assets. What do I have here? Assets. Here, config. Yeah, these are the. Do I have? No, I don't have anything here. So now I need to import that file that I just gave you. So I will go to my Dropbox, which is a mess, and I need to put some order to it. Config file, config here. What did I do? Here. Config. We have it here now. Yeah, we have. So we do ML agents, learn. We will provide the ARM config .yaml run ID equals to, and we will say like actually I need to change something before I go too crazy, but we will press it first. We'll say like run 01. I need to update my behavior, my robot, because that's how we call our behavior. So it's saving. So remember always to put your behavior with the right name. In our case, if we go to the ML agents game object, it's called my robot. So now we're finally good to go. I press enter. Hopefully it won't give me like a YAML error. It's taking a while. I'm scared. Please don't break. Okay, now it's all right. It's ready to start training. So it's not doing anything. Quack, 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 quack. Let's see why. Did I forget to put something here? It is not doing anything for some reason. We have the action set correctly. Behavior type, it's okay. Oh, this is weird. Why are you not moving? Let me see if, yeah, it's not doing anything because we should, if we go to my robot, we should see this changing. So probably this is not connected. I have many instances of, there is a problem with the connection to the actual workload. So let me close everything so I don't have anything interfering with this, because I want to show you the last thing. So we are okay today. Just in case, I will copy this so I can reuse it. I will deactivate my environment. I will activate it again. Conda activate the F workshop. Good. Now let's see. It will give me an error that that configuration already existed. It's listening. Oh, I know why. We forgot one specific thing, the decision requester. Damn it. Decision requester, we will crank it up to 20, to the maximum. And now when I press this, it should start doing stuff. Of course, it was not taking any decision, poor guy. There we go. Ta-da! Our robot is finally training. And you can see that the joints are going crazy with information, like the speed that this guy is moving, the velocity, the inertia tensor, and things like that. And it's giving you like, it's also changing the rotation state that we were passing in the actions, like positive, negative, and you can set more speed or less speed. So it's still not doing anything. And I think it's weird that this is not, oh yeah, now you see it touch it. I can force it for the first time to touch. So it touch it, so you can cheat a little bit that it trains. Basically it gets the reward for touching and then it changes immediately to another position. So I will go again. So you see that it will change position to another once it touches it. Is it? Yes, it changed to this position. So it's picking a random position. So it knows how to go. So imagine if you're building a wall, you can set a new position each time. That could be like a different script. But for now, we're just forcing it to behave correctly. So a couple of things. If you see that it's not going vertical, probably you want to invert the vectors in the actions. Probably I messed up. One more thing that I want to show you, that it's actually getting a lot of reward. That is surprising. That should not be happening. So probably I want to decrease the rewards, and I don't have many negative rewards. So that's okay. It doesn't matter for this training. I will provide also a train file so you can play with it. But I want to show you the last thing is that you can visualize the training not only there. You can, let me go to my, dear, city space, desktop, DF workshop, CD day 4, CD robotic arm, config, and let me show you the content of config. You see now that you have a folder that is called results. So if you go inside results, you will see that now we're running ron02.beta. So for this, you can do TensorBoard. Remember, you need to be in your an account environment. You can have like many. You can use the environment in many terminal windows. So I can say, I have that line somewhere here. Yeah, you can do TensorBoard log dir directory, and pass the name of the directory. So in this case, it's ron02. And this will open a local server. So it says that TensorBoard 2.2.2 is working in this thing. So I copy this address and I can go to, for example, Chrome. I can go to Chrome, and Chrome will start showing you in real time the evolution of your training. So this is just like every time that you use TensorFlow or PyTorch, and if you configure it accordingly to check how things are going, you will have information about, for example, the reward or the cumulative reward or the episode length, or if it's training, the loss, the policy loss, the value loss, and policy information, like a lot of things that are, for example, if you want to check, and if you see something that is not going very well, you can just tune your parameters. So yeah, you see that the robot is actually learning to go around. It doesn't see yet the target like many times, but probably I just mess it up with the rewards. Check the other script that I provided, and it will be fine. It should work okay. Also, the other thing that I don't know. Oh yeah, I have a mesh collider, so you want to set it to convex. No, sorry, to normal for the plane. So it actually clashes and don't go under the floor. So that is pretty good. I mean, so far we have trained. It takes time, so I will leave the training up to you. So far, we trained 3 agents. The drone, I think, is the most difficult one. So, but I needed to show you that. I'm still like tuning it, and probably I will provide a better version for it later. The cube, I saw that many of you train it. So it will be a cool thing in the future for you, because again, this is not a project-based workshop. I hope that you can do the training and send me those projects. Hopefully, like share the Unity project, because they are asking me from the conference to do that. Share it so I can send it to them, because they're asking me like 3D files. So if you send me a video, it won't work. So if you can share the Unity project, that would be nice. But imagine ways in that you can make these objects interact, right? Now we have all the ingredients, let's say, if we train this. It won't be like a crazy thing to, for example, if we have the first agent that we train, the cube, for example, if this is the cube, and make the cube go pick something, then travel to a specific location and drop the thing that just picked, and the robot pick this and give it to another one. Or have 2 robots collaborating, and one robot picks, grab one thing, leave it, the other picks it and build, or 2 build a wall or things like that. So they're like, the possibilities are endless. So you see that now the robot is doing kind of crazy stuff, but I think it's improving in time. So let's see how that turns out. Yeah, I extended a little bit, but it's okay. I have a couple of problems for the final session, so I have a proposition for you, if that's okay. I mean, it was a lot to cover for this 4 past session. Tomorrow I have overlaps with a lot of things. I cannot do a final session. I have 2 classes to teach. I have meetings. So I was trying to think in a good time in order to do the 5th session. So that wouldn't be impossible. So what I will do, I will record the final session where I will try to implement a collaboration between 2 robots, explain how it's done, because this is not machine learning stuff. It's just like Unity things that I need to cover. And I had prepared something also to explain the other type of algorithm. So one thing that is also missing that I promise is how to do reinforcement learning. So that I will provide, and I will upload both in my YouTube channel, because I know that Saturday, some people already told me, because I email, it's a problem because it's 4th of July. Also tomorrow is a day off in the US. And the other thing is that, yeah, on Saturday it will be a little bit difficult for me as well, because it's also a family day. So nevertheless, I mean, for me, it has been like a lot of work. And again, I mean, doing this on my own has been like also great to review a couple of things that a couple of things that I did in the past. So it has been fun. It's helping me a lot, this Unity things. For my own research, I work with other tools. I never use ROS, for example, but I'm learning how to use that. I use something that we use here at MIT that is called PyDrake, that is from one professor from the locomotion robotics group. But I think that this is a great tool also that I can use for my own research. I'm building my own robotic arms, since we have like just small ones at MIT and everybody wants to use them. So I don't know, I will show you what comes out from this, and hopefully you can share also the information. That's the idea. And I think that was also the idea, probably you will hear for the closing ceremony, that the idea was to, given the circumstances of this pandemic, was to share knowledge. And when they asked me like the first time, I said yes, because I love teaching. I hope I was clear enough, and also to share this type of things that hopefully, like some of you, I mean, I know that some of you know more than me in this type of stuff. I don't know much, but it was great to share, and hopefully we can share experiences from this thing. So we won't have another 5th meeting, but I will upload the videos. I promise. I will put this project, this specific project, on GitHub right now, and hopefully you can, GitHub, on Dropbox, and hopefully you can share. If you can make a folder, I will give you edit permissions where you can upload what you did with this, so I can share it with the digital futures part people. So I will stop sharing. I don't know if anyone has like more like questions. If you have questions, also you can always reach me by email or Instagram. I know that some of you are already following me, and I Instagram a lot. Some people are annoyed by that, but I mean, it's a good way to keep communication and to show stuff. Facebook, I don't do, even though I have an account. Twitter, I do. If you look for me, you will find me. But email is a good way to reach me, or messages through Instagram. Email, I will try to answer. And we can set meetings later as well. So I have no problem with that. Gladly, we can go over some other stuff. And again, if someday you're interested in collaborating or doing something together, just shoot me an email or give me a call, and that will be amazing. My Instagram account, Maria is asking, so is, I don't know what my Instagram account is. Let me check. I will check immediately. Actually, I was just sharing a story. So my Instagram account is just my name, Diego Pinochet, all without spaces. Diego Pinochet. And you can follow me. And also my YouTube channel, you have I share the thing. I will add more stuff. I started for the quarantine series, a series of tutorials, mostly on coding and things like that, things that people from like MArch students from MIT wanted to learn. But I want to do like this type of things. I love Unity. My dream is to make a video game one day. So probably you will see more stuff about that. So any last words?
Thank you.
Yeah, thanks a lot. This was a great workshop.
Tell that to the organizers so they invite me to do one again in the future. If you give me bad reviews, you won't hear from me for the next digital futures. So maybe we will have to see each other at some Acadia or any conference of that type. That is the typical thing. I never go to those, but I will try to go because those are fun. You see familiar faces.
Yeah.
Okay, so if there are no more questions, I thank you. Like I really appreciate your patience because and also being like a nice group of people, like learning, asking questions, and yeah, have a nice 4th of July if the ones that are in the US, and also stay safe and healthy. I don't know what's the situation in your current countries right now. In my home country, Chile is the worst of the worst. We're #1 in cases per million. And also in the US, it's a disaster still. At least Boston is doing great. New York's still doing pretty bad. Some people told me, and I have to go on Monday to renew my passport. So I will have to get a radiation isolation suit. So stay safe. And yeah, thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks. Bye.